Moving on to the next question for June 2022, P21 question 4. In question 4, we have a spring that is suspended from a fixed point at one end and a vertical force is applied to the other end as shown in figure 4.1. The variation of the applied force F with length L of the spring is shown in figure 4.2. Now, determine the spring constant K of the spring. Whenever we are dealing with spring constant, the first equation that will come to mind is Hooke's law, which is F is equals to Kx. Now, there are two ways to find out the spring constant K. The first thing that we could do is to probably equate the equation with the general equation of a straight line, y equals to mx plus c, where here we will be able to see that the y-axis is actually the applied force, the x-axis is actually the extension, and then finally we will see that the gradient is actually the spring constant. So here we will say that gradient is actually, let me just erase this, sorry. The gradient is actually the spring constant K. Now, if we were to plot a graph of force versus extension, like the ones that are shown here, it should be a straight line graph that passes through the origin. Okay, so we ought to be getting a straight line graph through the origin. Okay, so if we have a straight line graph through the origin, the gradient of that graph would actually be our spring constant K. So this is one way in which we can find the spring constant. Now there's also another different way in which we can find the spring constant. That one is actually just by saying that since force is equals to the product of the spring constants times x, the spring constant is therefore just the ratio of the force divided by the extension. So here, if we know the force that is applied, as well as the corresponding extension caused by the force, we would then be able to find out the spring constant. All right. Now, in our case, for the graph, this graph here is a bit different because this is not a force versus extension graph. Notice that this graph here is a straight line, but it doesn't pass through the origin. Now, the reason for that is because this is actually not a force versus extension graph. It's actually a force versus length L of the spring. So bear in mind that this is not extension X of the spring. We want to change this graph into a force versus extension graph. Now, looking at this graph here, we can see that the length of the spring is 20 centimeter when the force is 0. This would be the unstretched length. Anything after that would have been considered our extension X. All right. So if we want to produce a force versus extension graph now, it will probably look like this. So just give me a moment. We plot the axis of F versus X like this. So it by right should start from 0 because when there's no force applied, there shouldn't be any extension. So it will be a straight line graph through the origin. So this part here will be 0 for the extension. This part here will be 0 for the force. Now, it will be a straight line all the way to the end at 60 centimeter here for the length of the spring. This one would have been our final length. Okay. So what is our extension here? If we are talking about from 20 centimeter to 60 centimeter, our extension here would have been 40 centimeter. So for our graph, you go all the way up to 40 centimeter for force of 30 Newton. All right. Okay, so now this is our force versus extension graph. From here, we can now find out our spring constant. So let's just use the first method, which is from the gradient. So if we want to find out the spring constant from the gradient, we would actually just say that K is equals to the gradient. It will actually be 30 minus 0 over 0.4 minus 0. Remember to change the extension in centimeter to meter. So we will eventually get the answer as 30 divided by 0.4. So we have 75 Newton per meter. All right. Let's check whether the answer is correct. Yes, it will be 75 Newton per meter. All right. Now, instead of finding the gradient, this one is using the gradient method. This is using gradient. So instead of using the gradient, we can actually just use what we call a single point substitution, where we actually just find a value of force and the corresponding extension to find the spring constant. So in our case, we can actually just use this point right over here. We know the force is 30 Newton. We know the corresponding extension is 40 centimeter. So if we were to use the equation K is equals to F over X, we will be getting 30 divided by 0.4, giving us 75 Newton per meter. So this one is what we call as single point substitution method. This is single point substitution method. All right. Now it doesn't have to be the point at the end. It can be any point on the graph. So let me give you an example. If we were interested in, say, this point right over here, the extension of that point corresponding to that point will be 40 minus 20, giving us 20 centimeter. And then the force here at that point would have been 15 newtons. All right. So if we translate it to our graph, we are looking at somewhere around here, where our extension is 20 centimeter and our force is 15 Newton. So if we try to pick this point and use the equation K equals to F over X, if we sub it in, we get 15 divided by 0.2. We're going to get back the same exact answer. All right. So it doesn't matter which point we pick, as long as the point is on the graph itself. All right. So this is what makes single point substitution very useful. As long as you know what's the point on the graph, you will be able to find out the spring constant. Okay. So this one is for this question. Then I move on to the next one. For B, we want to determine the elastic potential energy in the spring when the applied force F is 15 Newton. When it comes to finding the elastic potential energy, we know that in general, it is actually the area under the force extension graph. Now, for a spring that obeys Hooke's law, as mentioned before, if we try to plot a graph of force versus extension here, it will be a straight line that passes through the origin. Now, if we define that elastic potential energy is actually the area under our fx graph, for a spring that obeys Hooke's law, the area under our force versus extension graph is actually this triangle right over here. So that EPE can actually be written as the area of a triangle, which is half fx. And then subsequently, we also know that F is equals to kx because of Hooke's law. If we were to put in kx here to replace F, multiplying it with x again, we're going to get half kx squared. So when it comes to finding our elastic potential energy, we actually have two equations that we can use. It's either half fx or half kx squared. Either one will allow us to find out the EPE. So now in our case, we want to find the EPE when the force is 15 newtons. And bearing in mind that we also know what is the spring constant, which we found from the previous part, it was 75 Newton per meter. So here we can actually use both of this equation to find EPE because we have the complete information. So let's start off with the first equation. If EPE is actually half Fx at a force of 15 Newton, the extension was actually going to be 20 centimeter. We actually did that just now. So extension of 20 centimeter would be 0.2, giving us 0.5 times 15 times 0.2. We have the answer as 1.5 joules. All right. So this one is if we were to use the equation half Fx. Now, if we were to do it another different way, we say that EPE is actually half kx squared. Since the spring constant was actually 75, and our extension right now is 20 centimeter, we take the extension, square it, we're going to get 0.5 times 75 times 0.2 square. We're still going to get the same answer of 1.5 joules. All right. So let's check the answer on the marking scheme. Yes, it is actually 1.5 joules. Okay. So let's move on to the next question. For question 5, a horizontal string is stretched between two fixed points A and B. A vibrator is used to oscillate the string and produce an observable stationary wave. So we are having a stationary wave right over here. Now, at one instant, the moving string is straight as shown in figure 5.1 below. The dots in the diagram represents the positions of the nodes on the string. Point P on the string is moving downwards. Okay, so whatever dots that you're looking at the screen right now, those are actually the position of the nodes. And particularly point P right over here is actually moving downwards. Now they tell you that the wave on the string has a speed of 35 meters per second and a period of 0.04 seconds. Explain how stationary wave is formed on the string. Okay, they're asking you for the formation of stationary wave specifically on the string. Now, this isn't asking you for the formation of stationary wave in general. It is asking you for the formation of stationary wave specific to the string, as stated in the question here. Now, if you recall how stationary wave is formed, generally they will tell you that stationary wave is produced when two progressive waves traveling in opposite directions overlap with the same speed and frequency. Okay, so the general definition for the formation of stationary wave was that stationary wave is produced when two progressive waves traveling in opposite directions overlap with the same speed and frequency. So some of the keywords that are usually present when you're talking about the formation of stationary waves is that they must be traveling in opposite directions, they must overlap, and they must be with the same speed and frequency. So in general, as long as your formation of stationary wave answer has these terms inside, it should be correct. But here, you cannot use it directly for this question because it must be specific to the string case right over here. So what you actually write will be something like this. The wave traveling along string is reflected. Let me just erase this, sorry. It is reflected at point B, which is actually our fixed point. Okay, so it is reflected at point B. Then the next thing we can say is that the incident and reflected waves traveling in opposite directions overlap with same speed and frequency, thus a stationary wave is formed. Okay, so some of the key points here will be using specific to the diagram, specific to the question. Wave traveling along the string is reflected at point B, or is reflected at fixed point B. This one will be 1 mark here. Okay, it's actually indicated in your marking scheme. Your wave traveling along the string is reflected at fixed point at A or at B or at the end there. And then after that, they mentioned that the incident reflected waves superpose and interfere, and the two waves traveling with speed in opposite directions superpose or interfere to give you your stationary wave. Okay, so they actually have bits and pieces from the general definition of formation of stationary wave. So we try to make our answer complete by writing everything in. So this is our model answer. Wave traveling along the string is reflected at point B. This is point number 1. And then for point number 2, we would have the incident and reflected waves traveling in opposite directions overlap with same speed and frequency. Thus, a stationary wave is formed. Okay, so notice that we have the keywords here: traveling in opposite directions, overlap with same speed and frequency. So we have our stationary wave. Okay, so this one is an answer that is above and beyond the answer that is given inside your marking scheme. It is giving you even more description. All right, so let's just have a look at what we mean when two progressive waves traveling in opposite directions overlap to give you a stationary wave. If you just look at the animation that I'll be playing soon, if you were to look at the video animation here, this is showing you the formation of stationary waves. There are 3 waves here. You can see a green wave, a blue wave, and a yellow wave. Specifically, I want you to focus your attention on the blue and green colored waves. So let me just pause the video a little. Now for the green colored wave, this one here, you will notice that it will actually move towards the right once I resume playing the video. Whereas the blue colored wave right over here will actually move towards the left when I resume playing the video. So right now, let's just look at the motion. You can see green moves to the right, blue moves to the left. These two waves are known as your progressive waves because you can see that the wave profile is actually moving from one point to another. Now, in our case, the two progressive waves are actually traveling in opposite direction. And from what we know about formation of stationary waves, as long as you have two progressive waves that are moving in opposite direction and they are overlapping with the same speed and frequency, you will get a stationary wave. So the stationary wave that we have is actually the yellow colored wave that we are looking at right over here. So this yellow colored wave is our stationary wave. All right. Notice that it will not move towards the left. It won't move towards the right either. It just remains in place while oscillating up and down. So the wave profile isn't moving. That is one of the characteristics of stationary wave. So let me just continue playing the video. Just have a look closely at the progressive wave motion and the stationary wave motion. All right. We will revisit this again later in the subsequent part of the question. For part B, On figure 5.1, sketch a line to show a possible position of the string a quarter of a cycle later than the position shown in the diagram. If you look at the diagram, the string is in a horizontal position. We want to show the position of the string a quarter of a cycle later. So to predict the shape of the string later, it will be useful to refer back to the animation of the stationary wave from before. So let me change the screen a little. Now, if you look back at the video animation from before for stationary waves, recall that the yellow colored wave is actually our stationary wave. Now, if you focus your attention on the stationary wave, you will notice that there are a few points there that don't actually move. These points here are actually our nodes. It is the point where the particles don't have any oscillation at all. They remain fixed in place. Now, this stationary wave here can be thought of as the stationary wave that is formed on your string in the question right now. Now, if you're thinking about the string, you can then think of the string as being made out of row or particles. So let's just pause the video at the appropriate timing, like let's just say now. Now you see that the string is almost horizontal. This is as close to horizontal that I can post the video to. So if the string is made out of a row of particles, if you focus your attention to the region between the nodes, you can think of the region in between the nodes as having a row of particles as indicated here, A. Let me just draw the row of particles first. Just give me a moment to draw them correctly. You can think of the region in between the nodes as having a row of particles like this. I want to draw 5 particles here and label them accordingly. This one would be, say, particle A, B, C, D, and E. And then for the next set of nodes, I also want to draw again a row of particles. So this is 1, 2, 3, 4, 5. And then this one, I will label it as H. Sorry, this one is A, B, C, D, E, F, right? So this one should have been F, G, H, I, and J. Okay. Now, at this position here now, all your particles are actually aligned in a straight line. So this one is where T is equals to 0. Now, you focus your attention on the first 5 particles, A, B, C, D, and E. Notice what happens to these particles when I let the video play. The thing that I just want you to see is that you will notice that each of these individual particles will actually start to move downwards before going back up to the equilibrium and then continuing upwards to a new amplitude position before coming back down. Okay, so try to see this motion for each of these individual particles. You see that particle A goes down, it goes back to the equilibrium, and then goes up before coming back down. The same could also be said for particle B. It went down, it went back up to equilibrium before going back up and then coming back down again. So this motion is repeated for all the particles that you see right over here. Now, the only thing that is different here would be the amplitude for each of these particles. You will notice that each of these particles have a different amplitude. Amplitude, as you recall, is the maximum displacement from the equilibrium position. Each of these particles right now have a different amplitude. Okay. Now, for each of these particles, just now I mentioned that they actually went down before going back up to equilibrium and then going back up before coming back down to equilibrium. When they do a motion like this, this is already considered to be one cycle. So let me just indicate the equilibrium position here. This one can be considered as your equilibrium position just now. So your particles A, B, C, D, E went down, then it went back out to equilibrium before going back up and then coming back down to the equilibrium position. This is considered to be one cycle here. Now, in our case, when they oscillate like this, your motion can actually be divided or split into 4 separate parts. So let me just redraw your diagram properly here on the top right hand corner. So just now I mentioned that this one was your equilibrium. So your particles went down before going back up to equilibrium, continue going back up before coming back down to equilibrium, isn't it? So you can now consider this motion as being made out of 4 separate parts. So this motion here, if I were to redraw it into 4 separate parts, is something that looks like this. There's one motion downwards, followed by a motion upwards, and then another motion upwards before going back down. Okay, so this motion here, where it went down, going up and then back down, was one cycle. So this one cycle here can be thought of as being made out of 4 separate parts. This motion downwards, this motion upwards, this motion upwards, and then finally this motion downwards. So this one cycle here, you notice, can be split into 4 separate parts. So each of these parts here is actually a quarter of a cycle. This one is a quarter cycle. This one is a quarter cycle. This one is a quarter cycle. And so would this one be a quarter cycle. So just now your question mentioned that you want to draw the new position of the string when it is after a quarter of a cycle. So if you just let me pause the video again at an appropriate time when the string is horizontal like now, just now they told you that there's a point P that is moving downwards. Let's just assume that that point P is actually this particular point here in the middle that is about to move downwards. So let me use an appropriate color. Let me choose a more striking color here. Maybe I'll just choose light blue for this. Okay, so let's just consider this to be our point P from the question that was about to move down when the entire string was horizontal. So if you're talking about the string as having moved a quarter of a cycle, just now I told you a quarter of a cycle would be just one part here like this, because one cycle can be split out into 4 separate parts. Now, if you are talking about a quarter of a cycle, that would have meant that you're just moving downwards once for each of the particles, like this manner here. So all your particles, A, B, C, D, have now moved to these positions. This will be where they have moved a quarter of a cycle. All right. Now, at the same time, if you look at the particles on the adjacent pair of nodes, F, G, H, I, J, originally they were horizontal too. They were aligned in a straight line. When they move a quarter of a cycle, they will have moved upwards in this manner. This is them moving a quarter of a cycle to these respective positions right over here. So this pattern here, you will notice, forms a sinusoidal curve. It forms a sine curve here, isn't it? So if you were to look further down the string, this pattern ought to repeat itself. So you're getting an even longer sinusoidal curve here, all right? So if you are asked to now draw the shape of your graph, shape of your string, it will now actually look like this. Let me just zoom back to the question. So on figure 5.1, sketch a line to show a possible position of the string a quarter of a cycle later than the position shown on the diagram. So we have this horizontal line representing our string, And then these dots here were actually our nodes, and point P was right over here in the middle. So if we already know that point P on the string is moving downwards, a quarter of a cycle later, it will actually just move downwards like this. And then another quarter cycle later, it will move upwards. And then another quarter cycle later, it continues to move outwards before finally moving downwards again to the equilibrium position after another quarter cycle. So when it moved like this one was considered one cycle for us. So we are just interested in a quarter of a cycle. So all those particles on the first pair or between the first pair of nodes, they all would have actually moved downwards like this. And then for the next pair of nodes, the particles will have actually moved outwards to this position here. So you repeat the pattern, you're going to get a sinusoidal curve like this. So let me just redraw them properly for you. So you're going to get a graph shape that looks like this. All right. So the marking scheme mentioned that you should have a approximate sinusoidal shape with maximum downward displacement at P and zero displacement at each node. Okay. So recall that the nodes are actually the points where the particles don't move at all. So the displacement will always be zero. Okay. So this is the shape of the graph that you're expecting to see. All right. And then from there, in part C, they want you to determine the horizontal distance from A to B. Okay, now from A to B here, there's one thing about stationary waves that you will have learned. For stationary waves, it was mentioned to you before that distance between adjacent nodes is equal to half a wavelength. So distance between adjacent nodes is always going to be equal to half a wavelength. So recall that in our question here, all these dots that I've just marked out in red are actually the position of our nodes. So if distance between adjacent node is actually half lambda, that would mean something like this. This one is half lambda. This one is half lambda. This one is half lambda, and half lambda. So from A to B, you count how many half lambdas do you have? You actually have 5 half lambdas. So over here, we will say that AB is equals to 5 half lambdas. But we can't proceed from here because we do not know what is our wavelength. So we have to find our wavelength first. So I shouldn't have written this first. I should have tried to find the wavelength. Now our wavelength can be found from the information given here, where we know the speed as well as the period. So if we use the equation V is equals to F lambda, the speed is 35. Frequency can be changed to 1 over T is the reciprocal of the period. So let me just rewrite this, sorry. Let me just rewrite this as P equals to the reciprocal of your period times lambda. Before subbing in your values, this one will be 35 equals to 1 over 0.04 times lambda. So in our case, lambda would be 35 times 0.04, giving us 1.4 meter. Now, just now it was mentioned to you that AB is actually 5 half lambdas. So now that we found lambda, we can now sub in the values. It will be 1.4 divided by 2, giving us a final answer of 5 times 1.4 divided by 2, 3.5 meter. This would be our final answer. So let's check the answers from the marking scheme. Yes, it is 3.5 meter. You're supposed to use B equals to F lambda, find out what is lambda, and then knowing that the distance A and B here is actually 5 half lambdas, you're going to get 3.5 meter. All right, so that's for this question. Then if you move on to the next question, which is in part D. Now for part D, they mentioned that a particle on the string has zero displacement at time t equals to 0. From time t equals to 0 to 0.06 seconds, the particle moves through a total distance of 72 millimeter. Find out the amplitude of oscillation of this particle. They want you to find out the amplitude of oscillation. To find the amplitude of oscillation of the particle, again, it will be useful to refer back to the animation of the stationary wave from before. Let's just change our view to the animation. Now, to find the amplitude of the particle after it has oscillated for a total time of 0.06 seconds, it will be useful to refer to how the particle oscillates in the first place when it was a stationary wave. Now, earlier in the question, it was mentioned that the period t is actually 0.04 seconds, okay? And now our particle has taken a time of 0.06 seconds when it was oscillating, and they told us that the total distance was actually 72 millimeter. From here, we're supposed to find out the amplitude of oscillation. Now, earlier, just now in the question, I mentioned to you to visualize how the particles on the stationary wave would actually oscillate. So I'm going to redraw some of the things here again. So earlier just now I told you that there are a row of particles in between the nodes. So this one would be particles A, B, C, D, and E. So let's just write it down as A, B, C, D, and E here. Okay, so they didn't really single out any particular particle. It could be the particle at the antinode position, or it could be a particle at some random position. Okay, the only thing we know was that a time of 0.06 seconds has passed, and the total distance moved by the particle was 72 millimeter. So we want to find that amplitude for that particle. So just now earlier I mentioned to you, each of these particles here, they will only oscillate up and down. And when they're oscillating up and down, they will actually complete one cycle. So I mentioned to you, if originally the position was that the particles were going downwards, let me just pause the video again, the appropriate timing when the string is horizontal and particles are going downwards, like now. So this was when the strings were horizontal, and then the particles are now moving downwards. All right. So I mentioned to you, for any of these individual particles, if this one was the equilibrium, the particles, if they were to complete one oscillation, they will go down like this before going back up to equilibrium, and then going back up to a new amplitude before going back down to the equilibrium position again. All right, this is what makes one cycle. And then further to that, I mentioned to you that when the particle was moving in this manner, you can actually split up their motion into 4 separate parts. The first motion down like this, second motion up, and then third motion up, and fourth motion down. So it can be split up into 4 separate parts. Okay. So now, how does this relate to finding the amplitude? Now, in our case, we can actually say this. We find out how many number of cycles has the particle actually moved. So I'll just write the workings here in yellow. Number of cycles that the particle would have moved would have been 0.06 divided by the time for one cycle. We are going to get the answer as 0.06 divided by 0.04. We are going to get 1.5. cycles. All right. So how many separate parts would 1.5 cycles actually have? You can see here, one cycle gives me 4 separate parts, isn't it? So from here, you can deduce that half a cycle must give me 2 separate parts, isn't it? Now at 1.5 cycles, this would tell me that I would have 6 separate parts. So right now, each part here would have represented the distance moved from equilibrium, the maximum distance moved from equilibrium. So each part here would have given us the amplitude. Okay, because you know that amplitude is the maximum displacement from equilibrium position. So if we were to split out our motion for one cycle into 4 separate parts, the distance traveled by each part is actually our maximum displacement from equilibrium. So therefore, it will be our amplitude. So now in my case, if I want to find the amplitude, it would thus be 72 millimeter divided by 6 separate parts, giving me 72 divided by 6, giving me 12 millimeter. Okay, because here 1.5 cycles or 6 separate parts, the total distance moved is actually 72 millimeter for the total distance. So if I take that 72 millimeter, the total distance, divide by 6 separate parts, that will give me the total distance moved for one part alone. So the distance moved for one part is the maximum displacement from equilibrium. It will be my amplitude. Okay, so that's why I take 72 divided by 6 here. I divide the total distance by the number of separate parts. That will give me 12 millimeter as the answer. So if I just move back to the question, this would actually be the workings. All right, so because if I go and shift back to the question later on, these workings will all be gone. This would have been the working for your question. All right, so if you want to copy, you should copy this. All right, the reason why I'm showing you this animation is so that you can easily understand the workings. All right, so I'll move back to the question. So calculate the amplitude oscillation of the particle. The answer was actually 12 millimeter. Okay, so you notice that in the marking scheme, they actually take 0.06 divided by 0.04 to get the number of cycles that has actually been moved. Then from there, to get the amplitude, we take the total distance divided by the number of separate parts. So we are going to get the answer as 12 millimeter. All right, so this is for this question. Now for question 6, state Kirchhoff's first law. This is pretty straightforward. Now Kirchhoff's first law tells you that the total current into a junction is equal to total current out of the same junction. Okay, now you need to be careful to always put in these keywords: total current or sum of currents. Okay, total current into a junction is equals to total current out of the same junction. Now you just said current into a junction is equals to current out of the same junction, you won't be getting the marks because you need to specifically write the keyword total current or sum of currents. Okay, now if you try to express this in an equation, it actually just means this: sum of current into a junction is equals to sum of currents out of a junction. Okay, so that's for this particular question. And then for part B, we have a battery that is connected to two resistors X and Y as shown in the figure below. The resistance of X is greater than the resistance of resistor Y. Okay, so this is one important information. Rx is more than Ry. Now from here, state and explain which resistor actually dissipates more power. Okay, so when you're talking about power dissipation, we are aware of three different equations. P is equals to VI, P is equals to I square R, and then P is equals to V square over R. So how would we explain the power dissipation? Which equation would we use? Now, there's one thing here that is useful to take note of. Your resistor X and Y are connected in parallel. So this one is the first thing that would be noticed. So you can say that resistor X and Y are connected in parallel, are connected in parallel. Therefore, they have same PD. Okay, because X and Y are connected in parallel, they would have same PD. Just to give you an idea of what I meant, if your EMF here is 12 volts, if you apply Kirchhoff's second law for this loop, this green color loop here, you only have one EMF and one PD here. So this PD here would be 12 volts. And then if again you apply Kirchhoff's second law for the second loop, which is indicated in blue here, again you have only one EMF and one PD. So this PD here must be 12 volts. So you make a comparison between the PD of resistors X and Y, you will notice that they are actually the same. That's why here we can say that when resistors X and Y are connected in parallel, they have same PD. Okay. Now from here, it makes your life easier because you know now V is constant. So you look at the equations with V inside, we have P equals to VI and P is equals to V squared over R. Now, we don't know anything about the current. We know something about the resistance, where resistance of X is more than resistance of Y. So we will actually want to use this equation instead. Okay, we won't use the first equation because although we know that the voltage is constant, we do not know anything about the current. Because you can see from here, if there's a current coming out from the battery, the moment it reaches this junction here, it will split up. Okay, so the current here at the top will be Ix going through resistor X. The current at the bottom here will be Iy going through resistor Y. We do not know the relation between current X and current Y. So we won't use anything that's related to current here because it only means that we need to do extra work. So we make use of something that's really given and really known, where we know that now resistance of X is more than resistance of Y. So we use the third equation here. If we use the third equation, we can see that P is equals to V squared over R. So V is constant. Therefore, P is inversely proportional to R. Okay. And then after that, you can then say that since Rx, we want the one with higher power dissipation, okay? So if you just look at the statement before, I said that power is inversely proportional to resistance. Your power will increase when R drops, okay? P is inversely proportional to R. Power would increase when R drops. So now you want to find the resistance that's actually the lower value here. The lower value resistance would actually give you a higher power. So here I can say that since Ry is less than Rx, Therefore, resistor Y dissipates more power. Okay, so we can check this with the marking scheme now to see what they write. The marking scheme just wrote something like this. Same potential difference across X and Y as they are in parallel. That's why I mentioned the first statement. And then after that, I say that you can use the equation power equals to V squared over R. And then since Ry is less than Rx, so Y dissipates more power. Okay, they didn't really explain the full story. They only explain bits and pieces of it. So the answer that I wrote here is actually the full story. Okay, so that's for this particular question. Then we move on to the next part. Now for the next question, in part 2, the two resistors are made of wires that have the same length. Both wires are made of metal of the same resistivity. State and explain which resistor is made of wire with larger cross-sectional area. Okay, so they've already mentioned to you that the wires have same length, same resistivity. Now, whenever you hear mention of length and resistivity in the question, the only equation that would actually relate to those quantities would actually be R equals to rho L over A. Now, you look at the question, they say same length, same resistivity. We can actually say that rho and L constant, R is inversely proportional to area. So when R is inversely proportional to area, if R is big, A is small. On the other hand, if R is small, A would be big. So they want the one with larger cross-sectional area, which means we're looking at this. We want to find the resistance that's actually the lower value out of the two. Okay, so in our case, we already know that Ry is actually the lower resistance. The resistor Y will actually be having a larger cross-sectional area. Okay, so how will we write our answer? You can actually write the answer according to what I've written on the right hand side. But let me just write out the sample answer for you. R is equals to rho L over A. So rho and L constant. Therefore, R is inversely proportional to cross-sectional area. Okay, is inversely proportional to our cross-sectional area. And then after that, we can again say something like this. Since Ry is less than Rx, therefore, resistor Y has larger cross-sectional area. Okay, because from this relation here where we say that R is inversely proportional to A, we know that if R is small, area will be big. Okay, so again, let's just check the answer with the marking scheme. The marking scheme would say something like this. R is rho L over A. Since Rx is more than Ry, therefore Y is suddenly the larger cross-sectional area. They didn't give you the full story. Again, they just gave you bits and pieces of it. So the workings that I wrote here would actually give you the full story. Okay, so this is for part 2. Then let's move on to the next part in the next page. Okay, for the next part C, a battery of EMF 9 volts and negligible internal resistance is connected in series with a light-dependent resistor LDR and a fixed resistor of resistance 1800 ohm as shown in the figure below. A voltmeter is connected across the fixed resistor and the reading on the voltmeter is 5.4 volts. Calculate the current in the circuit. So what we know is that this voltmeter connected across your fixed resistor is giving us 5.4 volts. we want the current in the circuit. Now notice that the connections here are all in series. You don't bother about the voltmeter because the voltmeter is actually connected in parallel and it actually doesn't draw any current. So you're just singling out the current flow inside the circuit. It is actually just flowing in this loop, this orange colored loop here. Okay, so let me just mark out the current. So current flows out from the battery. Let's call it I. It flows like this. It will flow through the fixed resistor. It will flow through the LDR before moving back in. It doesn't flow into the voltmeter because the voltmeter is not supposed to draw any current. Okay. So right now, notice that if we want the current inside the circuit, we could have actually just find out the current inside the fixed resistor itself. Because here you see the current is flowing in a series circuit. So in a series circuit, the current everywhere would be the same, okay? Because the current never branch out in the first place. So we want to find out the current flowing through the fixed resistor here. We already know the resistance R, we already know the voltage V. We can actually use the equation V is equals to IR, where V is 5.4, I is what we want to find. The resistance is 1,800 ohms. So our current will be 5.4 divided by 1,800, giving us 3.0 times 10 power minus 3 ampere. Okay, so don't write your answer as just 3. Instead, write it as 3.0 because your answers for paper 2 must be minimum to SF. Okay, so our answer here is 3.0 times 10 power minus 3 ampere. So let's check the answer whether it's correct. Yes, it is 3 ampere. Okay. Then after that, we move on to part 2. Part 2 is asking us to calculate the resistance RL of the LDR. We want to find out what is the resistance of this LDR here. Okay. So to do that, there's actually 2 different ways of doing this. Either we can use a potential divider equation or we can just use the equation V equals to IR in Kirchhoff's second law. So I'll just show you both here. Now, recall that I told you that this is a series circuit and that the current flow throughout the circuit is actually just confined within the orange colored loop. There's actually no branching of your circuit. It doesn't branch out anywhere. It doesn't split up anywhere. Now, specifically, I just want you to look at these 2 resistors here, the fixed resistor and the LDR. If you want to use potential divider equation where we say that V is equals to R1 over R1 plus R2 times V in for circuit like this, where this one is R1 and then this is R2, and then I want to find this V. Remember that I mentioned to you that time, to be able to use your potential divider equation, you need to have the same current through all the resistors involved. So in our case, you can see that the fixed resistor and the LDR actually have the same current flowing through them. You can actually use potential divider equation. Okay, so you can use potential divider equation. All right. So if we apply potential divider equation here, I can actually say that V is equals to R over R plus RL times V in. V in is actually our EMF for my battery. So if I sum in the values now, this one would be 5.4 equals to 1,800 over 1,800 plus RL times 9. Then this one will work out to 1,800 times 9 divided by 5.4. This one will give me 1,800 plus RL equals to 3000. So RL would therefore be 1200 ohm. That's my answer. Okay, so this one is using potential divider equation. All right. Now there is another way to do this also. That one is just by using Kirchhoff's second law and V equals to IR. So there's another method here that I'll show you. So if you look at the same circuit again, just now it was mentioned to you that this fixed resistor here is having a PD of 5.4 volts, isn't it? So you try to apply Kirchhoff's second law for this circuit here. From K2 law, our sum of EMF is equals to the sum of PD. Okay, that's the most basic expression of Kirchhoff's second law. So right now, we had two PDs here and one EMF. The sum of these two PDs will give us our EMF. So we already know in the first place that this one is 5.4 volts. We want to know what is this PD across our LDR. We already know our EMF also in the first place, so we can actually find out what is the PD across our LDR. So right over here, we will actually say that E is equals to VR plus VL. It will be 9.0 equals to 5.4 plus VL. So VL here would be 3.6 volts. Okay, so our PD here, we've already found it to be 3.6 volts. Okay, and when it comes to the current, because this is a series circuit, whatever current that we found originally will also be the same current flowing through our LDR. So the current here was 3 times 10 power minus 3 ampere. Okay, it is following the value that we found in the first part of the question. So it's 3 times 10 power minus 3 ampere. So now we know the voltage, we know the current. We can actually use V equals to IR to find out the resistance. Okay, so this one will be the second part. So second part would be using V equals to IR. So from V is equals to IR applied to LDR, we know the PD is 3.6. We know the current is 3 times 10 power minus 3. Then the R is actually our resistance of LDR. Our resistance of LDR would now be 3.6 divided by 3 divided by 10 power minus 3, giving us 1200 ohms. It's the same as what we found earlier. Okay, so let's check our answer and see whether it's correct. Yes, it is 1200 ohms. Okay, for your current question, they were using potential divider equation to find the answer. All right, so that is for this part. Okay, then we move on to part 3. Now for part 3, they mentioned this. The intensity of the light illuminating the LDR increases. By reference to the current in the circuit, state and explain the change, if any, to the voltmeter reading. Okay, so our light intensity is increasing. By reference to the current in the circuit, what will actually happen to our voltmeter reading right over here that's connected across our LDR? Sorry, connected across our fixed resistor. Okay, so we have to explain it based on current changes. So now, to do this question, we can actually say this. When intensity increases, LDR resistance decreases. Okay, because if you're talking about resistance of LDR, recall that there's a graph that shows the resistance with the variation of the resistance with light intensity. So this is the resistance of your LDR, and this one is talking about light intensity. The graph shape would generally be something like this. Okay, so this tells us that when intensity increases, resistance of LDR drops. Okay, so we're just putting it into words here. When intensity increases, resistance of LDR decreases. So when resistance of LDR decreases, what happens to the total resistance of our circuit? Because you can see from here, R total is actually the sum of the resistance of our fixed resistor and the resistance of our LDR. So if this one is fixed, or rather constant, but this one is decreasing, our total resistance obviously will have to drop. Okay, so here we would say that total resistance decreases, therefore current in circuit increases. Okay, so because total resistance has now dropped, the current in the circuit will now increase. And then there's a continuation to this answer, because here we want to explain how does the current actually affect the voltmeter reading. Okay, so the continuation to this answer right here on the left hand side here. So when total resistance decreases, current in circuit increases. So for the fixed resistor, B is equals to IR. R is constant, therefore B is proportional to current. Okay, so when current increases, B increases. Okay, so this one I can say, therefore voltmeter reading increases. Okay, so this answer is a bit long-winded, okay, because I'm trying to explain it. I say that for the fixed resistor, if you apply equation V equals to IR, the fixed resistance here is constant. So PD will be proportional to current. When your current flow increase, your voltage will increase. The PD across your fixed resistor will increase. Therefore, your voltmeter reading will increase. Okay, but let's look at how the marking scheme worded their answers. It's going to be pretty short for the marking scheme. They just say that resistance of LDR decrease, then current increase, so suddenly voltmeter reading increases. So again, they didn't really tell you the full story. Why did it actually increase? Okay, so you really want to get a full idea of how does it relate to each other, it might be better to copy the answer that I just wrote on the screen here. Okay, so this is for this particular question. There's one last question left for us to do. All right, for the last question on particle physics, you have an unstable nucleus XAZ that decays by emitting a beta minus particle. Describe quantitatively the changes, if any, in A and Z when X decays. So quantitatively here means you need to give some sort of numerical value, which means that you need to do some sort of calculation. Now, if you look at the question, A and Z here actually represent your nucleon number and proton number respectively. So right over here, if you look at A, this one is actually your nucleon number, where Z is actually your proton number. So the easy way to find out the changes in the nucleon number and proton number is to write out the nuclear equation. So right now, if I want to write out the nuclear equation, it will be X, A, Z. Let's just say that it becomes an element Y, and then you have a beta minus particle emitted, which is -1, 0. Okay, now recall that in any nuclear reaction, the total proton number and nucleon number is conserved. Okay, total proton number and total nucleon number is conserved. Okay, this means this proton number before and after remains the same, and then nucleon number before and after also remains the same. Okay, this is what we mean by proton number and nucleon number being conserved. If you look at the proton number before and after, it must be the same value. And then you look at the nucleon number before and after the reaction, it must also remain the same value. Okay, so right now, if you look at the nuclear reaction, we know that before the reaction, which is this one, our proton number is Z. But after the reaction, which is on the right hand side here, we notice that because of the beta minus particle, the proton number would have decreased by 1. Okay, so in order to offset this change, our proton number must have increased by 1 instead. It must be an opposing change. So for the proton number of Y, it will be Z plus 1. So because you see now, if you take Z plus 1 plus with minus 1, you're going to get back Z. Okay, your proton number here actually remains the same as before. Okay, so proton number after reaction will be Z plus 1 for the new element. And then after that, now you look at the nucleon number A. Now, after the reaction, if you look at the beta minus particle, there's actually 0 proton number there. So there's actually no change whatsoever. So when you look at the element Y here, your proton number ought to remain at A. So that A plus 0 still gives you A, the same as before. Okay, so right now, if we ask you, what are the changes in A, is actually 0. No change. But what about the change in Z? It will be plus 1. Okay, so let's check the answer. Change in A is 0, change in Z is plus 1. Okay, now in addition to your beta minus particle, another lepton is emitted during the decay. State the name of the other lepton that is actually emitted here. So for beta minus particle, we know that you're talking about beta minus decay. So this one would be neutron change to proton with the emission of your beta minus particle and an electron antineutrino. Okay, so remember to write in the proton number and nucleon number. So this one would be 0, 1, 1, 1, 0, 0. Okay, so our leptons would actually be these two right over here. So this one we already know is our beta minus particle. So let me just change the color a little. This is our beta minus particle, or in other words, our electron. Okay, so this one is our electron, and then the other particle here is our electron antineutrino. Okay, so the name of the other lepton here is electron antineutrino. Okay, now beta minus decay is this. What about beta plus decay? Now, for particle physics, it is very important for you to remember beta plus decay and beta minus decay. But one of the main issues that people face is they are confused which one should be which. Whether should it be neutron changing to proton first or proton changing to neutron first for the beta plus and beta minus decay. So there's an easy way to remember which is which. This is what I'm going to teach you now. So if you're talking about beta plus decay, it's actually proton changing to neutron, giving you your beta plus and your electron neutrino. Okay, so again, if I write down the proton number and neutron number, I will get 1 1. Sorry, this one is 1 1 0 1 0 0. Okay, so this one is our anti-electron or our positron. Okay, so then this one is our electron neutrino. Okay, now the easy way to remember whether should it be proton changing to neutron or neutron changing to proton is that you always start by remembering beta plus decay first. Now beta plus is positron, isn't it? So positron starts with P. So if it starts with P, then it is proton. Okay, so proton changes to neutron. That's the easy way to remember whether it should be proton first or neutron first. If you remember beta plus decay is positron, it starts with P, so it's proton first. Okay, so then the other one must be the other way around. So if it's beta minus decay, it will be neutron changing to proton. Okay, so that's how you can easily remember them. Now for part B, our particle P is composed of an up quark and a down antiquark. Calculate the charge Q of the particle P in terms of E, where E is the elementary charge, and then show your working. So what you have here is an up quark and a down antiquark. Okay, so when it comes to charges for your quarks, you need to remember them. There's a table for it from last time, but I'm just gonna give you the important ones relevant to your question first. Now, if you're talking about an up quark, your charge will be plus 2 over 3e. If you're talking about a down quark, your charge would be minus 1 over 3e. Now, if you then move on to a down anti-quark, it will actually be plus 1 over 3e. So what you should remember here is that antiparticles have opposite signs, okay, but same magnitude. All right. If you're going from a particle to an antiparticle, the magnitude of the charge will remain the same, but the sign would change. So if down quark is negative 1 over 3e, a down anti-quark will be plus 1 over 3e. Okay, the sign is just opposite. So right now we want to find out the charge of particle P here that's made out of the up quark and down anti-quark. We can just write something like this. The charge of particle P is actually going to be plus 2 over 3e plus with 1 over 3e, giving us positive e. So the charge is actually plus e, plus 1e. Okay, so let's check the answer whether it's correct. Yes, it is correct. So plus positive 2 over 3e plus 1 over 3e, giving you 1e. Okay, so this one would be your particular charges. Okay, now for the last question here, they mentioned this Particle P belongs to two classes or groups of particles. State the names of these two classes. Now, the most obvious group of particles that they belong to would be hadron. Okay. Hadron is actually group of quarks. Okay. Hadron is for group of quarks. It can be of any combination. As long as it's a group of quarks, it's called a hadron. Okay. Now, a more specific name for certain group of quarks that you will learn in your syllabus is meson and baryon. So in your case, this particle P here that consists of an up quark and a down antiquark is actually known as your meson. Okay, now meson is actually a pair of quark and antiquark. It's actually a pair of quark and antiquark. Okay, so if you see two particles, when I say a pair here, it really means two particles. If you see two particles and one of them is a quark, one of them is an antiquark, it would be a meson. Okay, so now if you look at particle P here, it consists of two particles. One of them is a quark, one of it is an antiquark, so it must be a meson. Okay, now there's another group of particles that you will need to learn in your syllabus. That one is actually your baryon. Okay, let me use a darker color here. So let me just erase this. The last group of particles that you need to learn is actually your baryon. Okay, now baryon is just a group of three quarks. So this one is group of three quarks. Okay, so you see three quarks grouped together to form one particle. That one would have been known as your baryon. Okay, so all these terms here actually relate to group of particles. So for hadron, hadron is actually a more generic name for group of particles. Meson and baryon is actually more specific in terms of the number of quarks involved and in terms of whether it's going to be quarks or antiquarks. Okay, now lately in 2022 onwards, they have started to test you particularly on these two terms. Last time, before 2022, they never really bothered to test you on meson and baryon, but from 2022 onwards, there's been quite a number of questions that keep testing you on whether you know what's a meson and what's a baryon. Okay, now when you're talking about baryon being group of three quarks, they might further ask you what is an example of a baryon. So example of a baryon, which consists of three quarks, is something that you actually have been dealing with a lot of times. An example of a baryon is actually your proton, which consists of up, down quark, and also your neutron, which consists of up, down quarks. So these have three quarks. They are also known as baryons, in addition to being known as hadrons too. Okay, so just bear all of this in mind before you sit for your exam. Okay, so with this, we are done with the last question. We already completed this paper.